dark matter and dark energy are top suspects in the cosmological crisis. Current models suggest that dark matter and dark energy together account for about 95% of the universe, but neither has been directly observed or proven to exist. They might not exist at all or perhaps have properties we do not yet understand. One idea under discussion is that these dark components' properties may have evolved over time, potentially indicating some form of intelligence. Gravity, which is supposed to cause attraction through mass or spacetime curvature, has not been definitively proven, although spacetime curvature ideas largely from Einstein have been validated numerous times. We cannot entirely rule out the possibility that gravity has different properties than we assumed or that another effect causes gravitational attraction. Over the decades, certain values in cosmology and astrophysics have been established as cosmic constants, believed to be reliable due to their stability. Calculations suggest that small variations in these constants could provide new insights into the universe and explain phenomena without dark energy. It is also possible that our interpretations of light shifts have been incorrect, leading to inaccurate distance measurements and galaxy ages. Perhaps our assumptions about the universe's initial conditions were flawed, or we misinterpreted the cosmic microwave background radiation. It might even be that the universe does not originate from a single starting point, challenging the Big Bang theory. Despite our technological advancements, minor errors in the Webb telescope or other observational tools cannot be ruled out. Engineers and scientists acknowledge that errors in instrumentation, data processing, or interpretation are always possible. The ongoing reevaluation of cosmological theories underscores a fundamental aspect of scientific progress: the ability to adapt and evolve our understanding in light of new evidence. The James Webb Space Telescope's observations are more than just a technological leap. They represent a pivotal moment in our quest to decipher the universe's mysteries. As we grapple with these revelations, it is important to recognize the broader context and implications of such scientific advancements. In cosmology, the process of refining theories is often driven by the need to reconcile observations with theoretical models. The discovery of unexpected phenomena or inconsistencies in established theories can be unsettling, but it also presents a valuable opportunity for scientific growth. Theoretical models in cosmology are constructed to provide a coherent framework for understanding the universe's origins, structure, and evolution. However, as new data emerges, these models must be tested and, if necessary, revised to accommodate new insights. One significant area of focus is the concept of dark matter and dark energy, which are central to contemporary cosmological models. Dark matter, an invisible form of matter that does not emit or absorb light, was proposed to explain discrepancies between observed galaxy rotations and the mass predicted by visible matter alone. Similarly, dark energy was introduced to account for the observed accelerated expansion of the universe. Despite their crucial roles in current models, both dark matter and dark energy remain enigmatic. Efforts to directly detect dark matter through experiments on Earth have so far been unsuccessful, leading researchers to explore alternative theories and possibilities. The challenge of understanding dark matter and dark energy is compounded by the vast scale involved in cosmological studies. Observations of distant galaxies, cosmic microwave background radiation, and other astronomical phenomena provide indirect evidence of these components, but their nature remains elusive. This uncertainty has prompted scientists to consider a range of hypotheses, from modifications to existing theories to entirely new paradigms. For instance, some theories propose that dark matter could be composed of more exotic particles than previously thought, or that dark energy might be a manifestation of a new fundamental force. Another intriguing aspect of cosmological research is the study of cosmic inflation. This theory posits that the universe underwent a rapid expansion in its earliest moments, leading to the large-scale structure we observe today. While inflationary theory has successfully explained many features of the universe, such as its uniformity and flatness, it also introduces questions about the nature of the inflationary period itself. Recent observations challenging established models of inflation could lead to revisions in our understanding of the universe's early history. Additionally, the search for extraterrestrial life continues to be a major driver of astronomical research. The discovery of exoplanets, planets orbiting stars outside our solar system, has opened new avenues for exploring the conditions necessary for life. Advances in telescope technology, such as the James Webb Space Telescope, enable scientists to analyze the atmospheres of these exoplanets for potential biosignatures. The possibility of finding life beyond Earth has profound implications for our understanding of the universe and our place within it. In the realm of theoretical physics, string theory and quantum gravity represent two prominent approaches to unifying our understanding of the fundamental forces. String theory suggests that the basic building blocks of the universe are not point-like particles but one-dimensional strings vibrating at different frequencies. This theory aims to reconcile general relativity, which describes gravity, with quantum mechanics, which governs particle behavior at the smallest scales. Although string theory remains highly speculative and mathematically complex, it has inspired new ways of thinking about the nature of space, time, and matter. Quantum gravity, on the other hand, seeks to develop a framework that combines the principles of quantum mechanics with those of general relativity. One leading candidate in this field is loop quantum gravity, which posits that spacetime itself has a discrete, granular structure at the smallest scales. This approach aims to resolve the apparent contradictions between the smooth spacetime of general relativity and the probabilistic nature of quantum mechanics. The interplay between theory and observation in modern astronomy highlights the dynamic nature of scientific inquiry. As our observational tools improve, our ability to test and refine theoretical models becomes more precise. For example, gravitational wave astronomy has provided a new means of studying phenomena such as black hole mergers and neutron star collisions, offering insights into the fundamental nature of gravity and the behavior of matter under extreme conditions. These discoveries have not only confirmed predictions of general relativity, but also opened up new questions about the nature of spacetime. In parallel, the field of astrobiology explores the potential for life in the universe by studying extreme environments on Earth and simulating conditions on other planets. Research into extremophiles, organisms that thrive in harsh conditions such as extreme heat, pressure, or radiation, provides insights into the kinds of environments where life might exist elsewhere. This interdisciplinary approach, combining biology, chemistry, and planetary science, enhances our understanding of the possible forms and locations of extraterrestrial life. A statement from Professor Carlos Frank, Durham University. I have devoted my entire career to developing a particular theory about the universe, and now this theory is being challenged. I welcome this challenge because it is through such scrutiny that we advance and progress in science. The James Webb Space Telescope is fundamentally disrupting many long-held beliefs in cosmology that have been accepted as truth for a century. A new ultra-deep image has revealed errors in our astronomical understanding. The telescope, initially designed to uncover the first stars of the universe, is instead questioning previous worldviews and may introduce an entirely new scientific paradigm. Not all researchers are wary of these new findings. Many scientists are actually embracing these developments. It has long been apparent that there were issues with our previous theories. The inconsistencies in measuring the universe's expansion rate alone should have raised alarms years ago. However, rather than correctly interpreting these warnings, many researchers clung to outdated theories. The cosmic microwave background radiation, CMB, which is the oldest light in the universe, was created about 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to form stable hydrogen atoms. This transition, known as reionization, rendered the universe transparent to light. The CMB was first detected in 1964 by American physicists Arnold Penzias and Robert Wilson, who encountered a persistent noise from every direction in the sky while working on new antenna technology. This discovery initially provided strong evidence for the Big Bang theory, earning Penzias and Wilson the Nobel Prize and establishing their finding as a cornerstone in the history of astrophysics. The CMB likely offers a snapshot of the early universe, with tiny temperature fluctuations providing critical insights into conditions shortly after the Big Bang. Scientists use the CMB as a reliable imprint to measure fundamental aspects of the material cosmos, including the universe's expansion rate. Edwin Hubble had already conducted such calculations in the late 1920s, observing that distant galaxies are moving away from us in all directions, with their speed correlating with their distance, a principle now known as Hubble's law or the Hubble constant. Although Hubble's measurements were groundbreaking, they were not as precise as those developed later. When the CMB was discovered, researchers recalculated the expansion rate, finding it significantly lower than Hubble's initial estimate. Subsequent recalculations using Type Ia supernovae as standard candles provided a more accurate measurement, but discrepancies remained. The difference in expansion rate measurements, known as the S8 tension or Hubble tension, has been recognized since the 1990s. Researchers have suspected that issues could lie with the CMB data, measurement methods, or the concept of universal expansion. This discrepancy suggests that our understanding of the universe might be fundamentally flawed. Since the James Webb Space Telescope began its operations, it has provided surprising data that could help clarify these issues. Galaxies so ancient and mature that their formation should theoretically predate the Big Bang are challenging old scientific theories. Astrophysics now faces what is considered the greatest crisis in modern astronomy. The expansion rate of the universe and the Big Bang theory are under scrutiny. Webb's images reveal a universe that significantly deviates from past models. The S8 tension served as an initial warning, and researchers who still adhere to outdated theories now face a dilemma. Many scientists are grappling with the realization that our knowledge of the universe may be inadequate, leaving many troubled and confused. To address this crisis, we must understand how science operates. Theoretical scientists use a combination of mathematical models, empirical data, and deductive reasoning to draw conclusions. Their knowledge comes from observed phenomena, experimental results, and theoretical analysis. The term theory itself suggests constructs and ideas rather than absolute truths. Our practical knowledge derives from images provided by telescopes, sound waves and radiation captured by radio telescopes, and data from neutrino and gravitational wave detectors. The James Webb Space Telescope allows us to break down the oldest light into individual frequencies and analyze it in unprecedented detail, revealing the prevalent elements in galaxies over 13 billion years ago, their mass, and the number of stars present. However, Webb's images may have limitations. For instance, it cannot always distinguish between galaxies and black holes that emit similar brightness due to massive accretion disks. Our scientific understanding has evolved to accept many eventualities as truths and has often dismissed alternative explanations. New findings from the James Webb Telescope offer crucial clues that may lead to replacing old theories with new truths. Scientists are currently grappling with these revelations, which seem so extraordinary that finding new explanations is challenging. The latest discoveries are shaking the foundations of physics, causing concern among many researchers. Physics teachings today are still heavily influenced by Isaac Newton's 17th century work. For 4 centuries, his laws of motion and gravity provided the foundation for understanding the physical world and the universe. Newton's laws effectively explain object movements under everyday conditions on Earth. However, in space, his ideas required expansion, largely accomplished by Albert Einstein in the early 20th century. Einstein's special theory of relativity, published in 1905, revolutionized the understanding of space and time, proving their relativity to the observer's motion. His general theory of relativity, published in 1915, extended these concepts with mathematical proofs of gravitational phenomena based on spacetime curvature caused by masses such as stars or galaxies. While Einstein's theories were coherent in many areas, he recognized their limitations and sought a unifying world formula without success. No researcher has yet succeeded in this endeavor. It is intriguing to consider where mistakes might lie. Michio Kaku, a prominent American astrophysicist, suggested that solving this problem could lead to a Nobel Prize. We need to investigate what facts scientists might have overlooked, whether there have been misinterpretations of phenomena, or if telescopes might be at fault. As our knowledge of the universe expands, so too does our appreciation for the complexity and interconnectedness of cosmic phenomena. The ongoing exploration of fundamental questions about the nature of reality challenges our assumptions and drives us to seek a deeper understanding. Each discovery, whether it confirms existing theories or suggests new avenues of inquiry, contributes to a more comprehensive view of the universe. In summary, the reevaluation of cosmological theories in light of new observations is a testament to the robustness of the scientific method. The James Webb Space Telescope and other advanced observational tools have provided unprecedented insights into the universe, prompting scientists to revisit and refine long-held theories. This process of continuous inquiry and adaptation is essential for advancing our understanding of the cosmos and addressing the profound questions that lie at the heart of cosmology and astrophysics. As we continue to explore the universe, we remain engaged in a quest for knowledge that not only seeks to answer fundamental questions, but also inspires future generations to push the boundaries of human understanding.